tengah hari sir. For today,
Hello.
I'm going to present about dynamic of machine tool. Um, both of my friend Muhammad Sharizal and also Ahmad Haki already presented about this topic. So now I, Daniel Luqman Hakim Khuzainal, will continue to present about dynamic of machine tool. What is dynamic of machine tool? For the introduction, it is about the machining accuracy depend on the precise machine motion under static and also dynamic and also thermal load. It is also the cutting force caused by an elastic deformation in the machine tool and also the workpiece. The deformation and vibration may lead to machining errors, reduce productivity, and chatter. First, we have to understanding the machine tool dynamic is essential to achieve high accuracy and also high productivity. So based on introduction, machine dynamic of machine tool is all about the uh, force that cause the elastic deformation for the tool and also the workpiece. We want to search for the accuracy so that we can increase the productivity of the workpiece. For the next slide, I'm going to talk about the machine tool elastic system. First, the machine behave as an elastic system due to the deflection under cutting force. The cutting process and also the motor process, friction process form a closed loop system. The interaction example as shown in the diagram, the two deflection change the chip thickness and also alter the cutting force. The friction misalignment carries tilting, change sideways friction. And also speed change affect the motor torque and change speed again. To two disturbance act on the system on elastic system. Show Y1 in bracket T, Y2 in bracket T, and also Y3 in bracket T on the working process. As shown, all the cutting process make the machine behave as an elastic system caused by the cutting forces. The forces bend or make the system elastic. The next slide. The equivalent elastic system. The full system has multiple interaction loop and also too complex to analyze. The working processes do not interact directly, only through the elastic system. The system can be simplified into a single loop system using EES. And EES represent either running machine, the motion without actual cutting. And next, useful for analyzing vibration, behavior, and system dynamic. As shown on the diagram, we have the equivalent elastic system connected to the cutting process. It shows a simplified single loop machining system. Next, we have the general procedure for assessing dynamic stability. First, on the left diagram, you have the stability of machine. You have the diagram of open loop system. It is a stability of machining evaluation using linear vibration approximation and also the vibration response defined by roots as shown as z equal to a plus minus iv. A is less than 0, it's equal to stable. And if the A is larger than 0, it become unstable, it become chatter. The higher order equation analyzed using the roof Hurwitz criterion, Niki's criterion, which is the most effective one to be used. But we also can use the root Hurwitz criterion. And also on the right, on the figure 4, we have the block diagram representing of a control system element. Shown on the diagram, it is a control system element with an input X in, and also it have X input, and also have output with each X out. It used to measure amplify the ratio and phase shift at different frequencies. It also provides frequency response data needed to construct the polar plot, which is very essential to step in building Nyquist stability analysis. As shown in this slide, we know that if A is lower than 0, the machine will become stable and more precise. But if the A is larger than 0, it's become more unstable and we can have chatter. Next, we have the Nyquist analysis and polar plot construction. As shown on the left diagram, A is the input and also the output signal. We show the positive and negative. B is the amplitude and phase frequency plot, and C combine into polar plot. And on the right, it show how two polar plot, EAS and also cutting process, are combined. Its amplitude value multiplied by A1 times A2 for each frequency, which is the phase angle added by theta 1 and theta 2 to form no angle. Resulting plot represent the open loop polar plot of the machining system. It is used directly for Nyquist stability analysis. As shown, this diagram help us to know and also help us to study more about the frequency of the system. Next, we have stability analysis, which is the purpose that we use. The purpose of stability analysis is also to carry out and also to determine whether the machine tool cutting process system operates smoothly or develop vibration. This is an unstable system lead to chatter, which reduce surface finish to life and machining accuracy. The relationship between the cutting process and the elasticity, which is the stability, depends on the interaction between the machine tool elastic system, EES, and also the cutting process. The dynamic characteristics such as stiffness, damping, and also the mass influence system behavior during the machine. Next, we have the chatter vibration. Instability in the system appear as self-excite vibration called chatter. Chatter cause loud noise, poor surface finish, tool wear, and reduced productivity. And the effect of undeformed chip width is also the cutting coefficient KS is directly proportional to the underformed chip width. As chip width increase, cutting force increase, raising the chance of chatter vibration. So now we know that we use stability analysis is to determine or to know the system can operate smoothly or not. Because if the system cannot operate smoothly, it also can increase the vibration. So we know that when the vibration increase, it is also directly causes by the width of the chip that we are making, because the wider the chip, the more forces that we need, and when there are more forces, So there is more force that make the system more elastic and raise the chance for charter vibration. Next, we have the single degree of freedom system, also known as static cutting process. The system description, in which is the system itself, the machine tool elastic system is modeled as a single degree of freedom vibration system. The cutting process is assumed to have a static characteristic as uh, the polar plot behavior. The open loop system polar plot is obtained by multiplying the ES polar plot with the cutting coefficient Ks, and only the amplitude change and the phase angle remain the same, as shown in the diagram. The stability outcome. The polar plot does not cross the critical 1 and 0 point. Therefore, the closed loop system is always stable under this condition, which is the it shows that if the polar plot cross the -1 and 0, it shows that there are more vibration in the system and shows that there is more cutter vibration that happen. Next, we have the engineering significance. Simple machine tool system with static cutting behavior are less prone to chatter, and it is very useful for basic machining operation and preliminary analysis. So we know that the simpler the machine with the cutting behavior are less prone to cutter. So when there is more part in the machine, there will be more part that can vibrate, that can become elastic, and also increase the chatter. So less part is better. And for the next slide, many degree of freedom system, which is still the static cutting process. It is a system that the machine is modeled with multiple degree of freedom using normal coordinates. This represent real machine tool more accurately. And also the polar plot characteristic. The ES polar plot consists of multiple loops corresponding to the different natural modes. The open loop system polar plot is obtained using static cutting characteristic as shown in the diagram, the polar plot diagram. It has two loops itself. And the stability result, despite multiple modes, the system remains stable because the polar plot still does not intersect the unstable region. And the practical importance is to show that complex machine tool can remain stable if cutting conditions are properly controlled. Confirm confirms the importance of static cutting characteristic in avoiding chatter. As shown in the diagram, it has two loops, but the polar plot doesn't exceed the stable region. And also, we know that if a machine or tool itself, we can control the movement or the precise movement, we can reduce the chatter.